Hey everyone, welcome back to Real Analysis 1. This will be lecture 16 of the course. And in this section, we want to spend a little bit of time discussing a particular class of functions, monotone functions, and characterize them a bit. Also look at how to construct an extremely useful example of monotone functions that will be used later in as a theorem tool later in some of the proofs. And then we want to discuss also discontinuities, so kind of an add-on discussion to whatever you would have had in calculus regarding discontinuities, the types of discontinuities, and then a characterization of these, but from a more real analysis, kind of rigorous standpoint. So let's go ahead and get started, jump into it. This will be section 4.4, monotone functions and discontinuities. And so let's start with, so to discuss discontinuities, we really need the idea of one-sided limits. So left-hand limit, right-hand limit. You will definitely have seen these in calculus, but let's define them for analysis. So definition, let's go ahead and let E be a subset of real numbers. And let's let f be a real valued function on E. So let P be a limit point of of E intersect, and then we'll say P to infinity. Okay. You'll see the importance of this in a second. Right? So P is a limit point of E, essentially. Then we say the function f has a, we'll say, right limit. It has a right limit at P if there exists some number L, real number, such that for all epsilon greater than 0, there exists a delta greater than 0, for which, and here's the basic thing, so f of x minus L is less than epsilon whenever P is less than x, which is less than P plus delta. Okay, so that's the definition of a right limit. Now the left limit, of course, is going to look very similar. It's just going to be a difference in this piece here. So this looks, this is, basically the usual definition of the limit, except here we specify that the limit point P is approached from the right, from the positive side. So, so that's why we say x has to be between the limit point itself and some delta distance, right? So you give me an epsilon, I identify a delta, and whenever x is within delta of P on the right, then the function has to be within epsilon of the limit. So very much the same as an overall limit, just directionally it has to be approached from the right. Okay, and so yeah, just to make that plain, so basically the regular limit says that f has to be within epsilon of L whenever x is in the delta neighborhood, right? So normally you could write, use the notation the delta neighborhood, or you could say P minus delta comma P plus delta. That's the same thing, isn't it? So this is overall limit. But here what we're saying is that x has to be in P comma P plus delta, right? So it's it's approaching from the right hand side. Okay, and so obviously when we're trying to prove things regarding right or left hand limits, we will use this as our assumption on the x values that drive this inequality, right, instead of this one, for right and left hand limits. And so left hand limit would just mean that x needs to be in p minus delta comma p, right? So in the left-hand side of the delta neighborhood. Okay. So this is right hand, and this is left hand. And that's the only difference, really. And then this is overall. Okay. All right. Notation on this. Well, you'll have seen certainly this notation, limit as x approaches p from the right-hand side would be kind of p plus of f of x. Another notation that will sometimes be used, not as often I wouldn't think, is the limit as x approaches p with x greater than p. All right, so this is kind of like the overall limit, except you're specifying also that x has to remain larger than p, so you're not approaching from both sides. Kind of a shorthand that we may use in proofs and when we're kind of reasoning about these things is f of p plus, right? So these are all the same thing. This is a shorthand. It's not very often used, but we will sometimes use it. And then, of course, all of the stuff on the other side, x approaches p from the negative side. And you could write that like limit as x approaches p where x is less than p. Or you could say f of p minus, if you want to be shorthand about it. Alrighty. And so that is the idea of right and left-handed limits. Now, it's useful to, in this context, describe what we mean by left and right continuity as well, right? So remember, we had the limit definition, and we had continuity, and they're pretty similar, certainly related. So here's the definition for right continuity. So let's let E be a subset of real numbers and F a real valued function on E. F is right continuous. It's right continuous at P in the set E if for any epsilon greater than 0 there exists a delta greater than 0 such that f of x minus f of p is less than epsilon for all x in E with, you named it, p less than or equal to x less than p plus delta. So the same definition essentially. The only difference here is specifying that we're in the right half of the delta neighborhood of p. We're not in the left half of the delta neighborhood of p when we're talking about right continuity. As we approach p from the right-hand side, these conditions have to hold. And the same thing can be said of left continuity, right? You just have to flip this inequality so that x is between p minus delta and p. Okay. All right. Okay. All right, so let's kind of jump into some theorems now and see what sorts of things we can see. Here's a theorem, and then we'll do some examples. We'll do one theorem and then some examples. So the first theorem, this one comes from calculus. We've certainly seen this in calculus. A function f on an interval AB, real value function on an interval AB, is right continuous at P in that interval if and only if f of P plus, so the right-hand limit of f at P, exists and is equal to f of P. Okay, so another way to say that would be just that the limit as x approaches P from the positive side of f of x is equal to f of P. All right, so this is the definition, this is the theorem that says right continuity exists if you have a right-handed limit and that thing is equal to the overall, is equal to the value of f at P. And the same is clearly true for the left side limits as well, right? So we'll just state the right-hand side, but the same theorem would apply to limits from the left. Okay. So this is a theorem that, I mean, so we won't prove this. You go back to your calculus books, you can see a proof for this guy, but we'll use it. We'll be using it in examples and later in theorems. But what we want to take a look at next are types of discontinuities. Okay, so types of discontinuities. All right, and so we talked about left-hand limits, left and right-hand continuity, left-hand, right-hand limits, left and right-hand continuity. And so when you don't have continuity, when you don't have a continuous function, you have some kind of a discontinuity. And there's fundamentally two types of discontinuities that you can have. Right? And so let's just restate what we just said, that f is continuous. F is continuous at p in some interval ab if and only if, that's what we said here, if and only if two things have to be true. First, f, the right-handed limit and the left-handed limit exist. Right, so you have to have a right-hand limit and a left-hand limit, and in order for continuity to be true overall, they have to be equal, right? So f of p plus equals f of p minus, which equals f of p, right? And so just to make sure, and this kind of defeats the purpose of having the briefer notation, just to make sure that you're following this notation, this is literally just the limit as x approaches p from the positive side equals the limit as x approaches p from the negative side, which is equal to f of p. Okay, so that's this is just this. Okay. So we know that f on some interval can fail to be continuous, obviously. And the reason it can fail to be continuous, as I said just a moment ago, it fundamentally kind of falls into two varieties, two types. And so the first one we'll talk about is what is frequently called a removable discontinuity. Okay, so the first type is the limit may exist, but it may not be equal to f of p. So you may have that the limit as x approaches p, the overall limit may exist, but not be equal to f of p. Okay, either f of p is something totally different, or maybe f of p is not defined. F may not be defined at p. Here's an example of that kind of thing. So if we say g of x equals, and this is one we've seen before, x squared minus 4 over x minus 2, and then we set this equal to 2. So when x is not equal to 2, you're at the top, and when x is equal to 2, you're at the bottom, right? And so what is the left and right-hand limit? So the limit as x approaches 2 of g of x from the right is equal to, well, you'd be approaching 2 for this function here, right? X is not equal to 2, but it's approaching it. And you can plug this in. You can do a little work on this, do some factoring and some canceling, and you'd see that this is equal to 4. And if you approach if you approach 2 from the left-hand side, you would get the same thing. Right? And so the left and right-hand side limits agree, but g of 2 is not equal to 4, it's equal to 2. Right? So here you have a left and a right-hand limit. They agree, but the value of the function at 2 is not what the limits suggest. So this would be an example of a removable discontinuity. Right? So this is, if you were to draw a picture of this, you've got some kind of function here, and for some reason, right at this point, the function just changes, it drops down. Okay, and so we'll say this is 2, and so maybe this is 4, and this is 2. right? So as you approach 2 on the function, it would suggest that the limit is 4, but the actual function is not valued 4 whenever x is 2. It's valued at 2. All right, so this is an example of what's called a removable discontinuity. Okay. So, the term removable is used because the idea is that you could make this function continuous just by changing a single point. Right? If we just redefined this as g of x equals x squared minus 4 over x minus 2 when x is not equal to 2, and then just set this equal to 4 when x is equal to 2, this is now continuous. Right? You just changed this one point. Right? So the function can be made continuous at x equals 2 by a redefinition at the point x equals 2. Just re-express it. Right? So this is what's called a removable discontinuity, because it's just one point. The left and right hand limits agree. It's just this one point. Okay, so that's the first type of discontinuity. The second type is what we would call, it's non-removable. Another way to think of it, which I think is better, is a jump discontinuity. So we'll say in this case, the limit as x approaches p plus of f exists. And the limit as x approaches p minus of f of x exists. But these two are not equal. Right? These two are not equal, and the picture that you're probably have in your head is something like this. You got a function kind of cruising along here, and there's a kind of an abrupt stop, and then maybe somewhere else there's a jump, and the function continues. Right, so there's this jump discontinuity here, and that's what I would refer to this discontinuity as, a jump discontinuity. Right, because the function kind of jumps. It's like the track of the function is not just missing one point. It's like all of these points here would have to be readjusted in order to kind of bring the function together. Right, and so this is what's called a jump discontinuity. Okay, it's also sometimes called a non-removable discontinuity. Okay, and so in the case when you have left and right hand limits, these are the two possibilities. Right, so just to reiterate, if fp plus and fp minus both exist, then the only two types of discontinuities are this guy, where you have fp plus equals f of p minus, but it's not equal to f of p, and this is a removable. And then the second one is where f of p plus is not equal to f of p minus, and this is a jump. So these are the two types of discontinuities that you can run into. Let's see an example of this jump discontinuity. So we'll say f of x is equal to x when x is between 0 and 1. And when it's outside of that range, it's equal to, 3 minus x squared. And we'll say that's whenever x is greater than 1. All right, so here this f is defined from 0 to infinity. And it's a piece function again, and here's what it does. Right, and so in this case, the function, what does it look like? So let's say this is 1, 2, 3, and this is 1, 2, 3. All right, so from 0 up to 1, it's just equal to x. And remember, notice it's inclusive of 1, so it's just the identity function there. But then once you jump at 1, there's this jump discontinuity, because if we were to plug in 1 here, you would see that this is 3 minus 1, so we would jump all the way up to here. So actually we'd have like an open gap there, and then it's basically going to come down and do something like this, right? It's a quadratic. It's 1/2 of a quadratic headed in the downward direction. So it looks like this, and so you've got this jump. So this is a jump discontinuity. Okay. Right, and so then we could say that what's the right-hand limit? So the limit as x approaches 1 of f of x. And so if we're approaching 1 from the right-hand side, we would be on this function, right? So that's going to be equal to the limit as x approaches 1, I should put plus there, of 3 minus x squared. And we can see that that's like 3 minus 1, so it's 2, right? What about from the other direction? The limit as x approaches 1 from the left-hand side. Well, if we're approaching 1 from the left-hand side, that means we're just here. So it's a limit as x approaches 1 from the left-hand side of just x, and we know that that is going to equal 1, right? And so these two are obviously not equal. So f of 1 plus is equal to 2, and f of 1 minus is equal to 1. And so these are not equal. So we have a jump discontinuity. Okay, so that's kind of a simple example, but useful to see how these things work, and it's very intuitive. If you've been through calculus, this will certainly be something you're used to. Let's take a look at a more complicated example. Not super complicated. One you may have also seen in calculus, and this is the greatest integer function. So f of x equals, and it's denoted like this sometimes. So it's like an x with the brace around it. And just to remind people of what this does, if I plug in something like 2.9, this would be equal to 2. And if I plug in something like 3.1, this would be equal to 3. And if I plug in something like 10.7, this would be equal to 10. So basically it's just sort of truncating, dropping all of the digits to the right of the decimal and just going with whatever the integer is. Okay. And so what does this look like if we were to plot this? Okay, so let me get some decent axes drawn out here. 1, 2, 3, we'll go to 4. Okay, and so whenever the number on the x-axis is between 0 and 1, and it's going to be like 0.5, 0.6, 0.7, and so the value will be just equal to 0, right? But as soon as it hits 1, it jumps, right? So it jumps up to here. So 1.0 would just be, the greatest integer would be 1, right? And it does this again on this interval, right? And then it does it again here. And then from 3 to 4, it does it again, right? It just continues like this. Okay, so this is the greatest integer function. Now notice you plug anything in here like 2.5, the greatest integer is 2, so that's why we're here on 2. So you can see that this is indeed what it looks like. So this function obviously has jumped at an infinite number of jump discontinuities, right? Every integer is a jump, right? So x has, the greatest integer function has a jump discontinuity at every integer. Okay. Right, because like notice that f of, like, so for example, if we approach 1 from the left, that's equal to 0. Right? If I approach 1 from the left, it's equal to, the limit is 0. If I approach 1 from the right, then the limit is 1. Right? So the left and right hand limits do not agree. Same is true for 2. If I approach 2 from the left, it's 1. If I approach 2 from the right, it's 2. Right? If I approach 2 this direction, then I'm on 2. If I approach 2 from this direction, I'm on 1. Okay, so every integer has a jump discontinuity. Okay, and so this function is a good one to introduce here because we'll use something like this when we construct our special function later in the section. Okay, and so these are discontinuities, and again, a lot of this stuff we've seen, but it becomes important. I mean, this section is important. It's also just interesting, but it will become important later in analysis. We need to be able to identify discontinuities, and we'll need to know what kind of discontinuity are we dealing with. Okay. All right, so let's shift gears now to monotone functions. This is a term you will have certainly heard, and you probably know what it means, but let's define what we mean by a monotone function. So let's let f be a real value function and we'll just say that f is defined on an interval. Okay. So we say that f, there's a couple of options here. F can be monotone, increasing, decreasing, or just strictly monotone, and or strictly monotone. And so we say f is monotone increasing on I if f of x is less than or equal to f of y, for all x and y in the interval where x is less than y. Right, so if x is less than y, then f of x needs to be less than f of y. Right, so for example, here's x, here's y, here's f of x, here's f of y. Right, so on an increasing function, you can see that when x is smaller than y, f of x needs to be smaller than f of y. That's monotone increasing. Now monotone, notice it says less than or equal to, so monotone functions can flatten out. You know, they can go up for a long time, flatten out a little bit, and then go up some more. They just can't go down. That's monotone increasing. And the same thing is true for monotone decreasing, except we just flip this piece, don't we? Right, so f is monotone decreasing if f of x is greater than or equal to f of y on I. F is monotone decreasing on I if f of x is greater than or equal to f of y, where x, again, is greater than y here. Okay, and so let's draw that out, make sure that makes sense. Right, so here we're saying that f of x is greater than or equal to f of y, where x is greater than y. So monotone decreasing function will look like this, and so here we've got, let's say that, so x is greater than y, so y would be here, x would be here, and so here's f of y, right, and then here is f of x, and so f of x, hold on a second, do I have that backwards? F of x is greater than or equal to y, x is greater than y. I think I need to write like this. Yeah. So if x is less than y, then f of y needs to be greater than f of x. Oh my gosh. So here we'll say, f of y is greater than or equal to f of x, where x is less than y. Right, it's just the reverse. One of the inequalities flips, the other one doesn't. So let's keep x and y organized as we have them, and let's do it like this. Okay, so it's like the reverse, right? So if And then we say f, and then we say overall f is monotone in general if 1 or 2 is true. This is just like a shorthand. Right? If it's a monotone increasing, we'll frequently just say, oh, that's a monotone function. If it's monotone decreasing, we'll say, oh, it's a monotone function. Right? Obviously, 1 and 2 can't be the same. They can't both be true. And so what we need is one or the other to be true, and we just call it monotone. Now contrast monotone with strictly, right? So strictly increasing is a thing also, right? So here we would say it's strictly increasing if f of x is less than f of y for all x, y, with x less than y. Right? So, and then decreasing would be the same thing. Just flip the inequalities. Right? So here, notice it's just, instead of less than or equal to, it's strictly less than. So this is a function that only goes up. It can never even level out. Okay. Now, it turns out monotone functions are more useful for our purposes than strictly increasing, but just notice that they're very similar. It's just this slight variation on this symbol here. Okay. All right. And so let's take a look at a theorem here for monotone functions. And I think this is pretty straightforward, but we will prove this theorem. So maybe the most challenging proof of this section. Let's let I be an interval of real numbers on the real number line. So we'll let it be an open interval. Let I in R be an open interval. And let f be a function on this interval, a real valued function. So we'll let I be a open interval in R, and let f defined on I into R be monotone increasing. On the interval, right? So f is a monotone increasing function on I. Okay, and there'll be a version of this theorem as well that's monotone decreasing, but we're going to write this one out, and then you can understand how the results would extend to monotone decreasing. Okay, and so then, if this is the case, then f of p plus, the right-hand limit at p, and f of p minus, the left-hand limit at p, exist for every p in I. And we have the following very useful inequality. The supremum of x less than p on the function f is equal to the left-hand limit as we approach p, which is less than or equal to the function evaluated at p, which is itself less than or equal to the right-hand limit of the function evaluated at p, which would be equal to the infimum of p less than x of the function. Okay. And we can say further, one little add-on here, if p and q are in the interval I, with p less than q, then it's going to be the case that f of p plus would be less than or equal to f of q minus, right? So the right-hand limit of p will have to be less than the left-hand limit of q. Okay, so let's break this apart for a second here. So in particular, let's talk about this section here. Like, what does this mean? Because sometimes this notation can throw people. When we say the supremum of x less than p, what is that? That's the supremum of the set, well, x is in I, the interval, and x is less than p. And the infimum x greater than p, that's equal to the infimum of that set. Okay, so it'd be x in I such that x is greater than p. Sorry, such x is greater than p. Yep. Okay. Right, and so just think of it like this. You've got some interval here, and p is right in the middle. And so everything over here this is the x less than p set. And this over here is the x greater than p set. Right, and so it's intuitive that the supremum, so what is the supremum x less than or p of f of x, sorry. Right, that's just, let's get the largest one, right? Let's go that way, get the largest one. What is the infimum? X greater than p of f of x. Well, that's the same thing. You're just going to grab, you're going to evaluate at the infimum, right? So you kind of come this direction, don't you? Right, and so when we say that these two things, so this would equal this we say that this is equal to the limit from the left. And we say that this is equal to the limit as we approach p from the right. It's just another way to say that, isn't it? Okay. All right. And we can kind of just because this people can benefit from just kind of seeing this visually. So I've got some function here, right, and I've got a p, right, and so this is obviously my f of p, isn't it? Right, so this is all x less than p, this is all x greater than p. Right, so in this case, the supremum of where x is less than p, f of x, in this case is equal to the right-hand limit. Okay, just like what we had said previously. But also it's actually equal to f of p. Right, which you can see that as you approach, and this isn't a hole, I should fill it in. I don't mean it to be a hole. That's not a hole in the function. But as I approach the supremum of x less than p, I'm going to, that'll be equal to the limit, right? And it's also equal to the point f of p, the value. And that's also going to be equal to the right-hand limit, in this case, which would be the infimum of the x greater than p f of x. Right, so in this case, it's just, this is what you see when you have like continuity, but what happens when you don't have continuity? All right, so let's say I've got a function that looks more like this. It kind of comes up, and then I've got a jump here. It does one of these, we'll say. All right, so again, here's my p, and this would be f of p. And this is all the places where x is less than p. This is all the places where x is greater than p. Okay, so in this case, the supremum of x less than p of f of x is equal to f of p minus, right? So as I approach p from the left, the value of the function at that x approaches the left-hand limit, right? Okay. Now what happens when I approach p from the right? Right. So that's the infimum of x greater than p of f of x. That's going to be equal to f of p plus, right? That's the limit. So as I approach, the infimum of this set of numbers over here is certainly going to be, the number that's closest to p here. And when I evaluate those, I'm going to get the right-hand limit. But in this case, as I approach from the left, this actually equals f of p, right? This equals f of p because it's defined there, but we got this hole at f of p on this upper piece. So then that means that this one, f of p, is less than or equal to these guys. Right, so just kind of wrapping this around here. Right, does that make sense? Right, you can see that this is less than, right? So f of p is down here. So, you know, this is less than that because it drops down. Right, now if this was a monotone decreasing function with a discontinuity, then you would have to flip this, wouldn't it? Instead of less than, it would be greater than, right? Because it would be heading down. It would look more like this. It would look more like this, right? And so then you would have this guy here. The right-hand limit is would be the reverse. Okay, so that's the theorem. It's basically just saying, well, look, if you've got a monotone increasing function, then you get this nice, useful inequality, which, as you can imagine, can just be plugged into a lot of proofs whenever you've established that you have a monotone function with left and right hand limits. You can plug this kind of thing in and get a long ways. So let's prove this theorem. It's going to be kind of a tricky one, but it is instructive. All right, so let's write the proof here. So we'll let p be a fixed value in I. So we're going to fix a p in I arbitrary. Let p be a fixed value in I. Okay. And since f is increasing on I, by assumption, since f is increasing on I, the set, here's our set, will be the set f of x such that x is less than p and x is in I. Since f is increasing, this set is going to be bounded above by f of p. Right, so this is all the x's less than p, so f of x, some x less than p, has to be less than f of p because f is strictly increasing, and these are all values that are to the left. Okay. Okay. And so we're going to call this set A. Well, hold on. No, we're not going to do it. So this is just the set. So this set is going to be bounded above by f of p. Okay, and what we're going to do is we're going to let A equal the supremum of this set. Okay, I hope that notation's all right. We're going to say that A is the supremum of all of these f of x values. Right, and so if the set is bounded above by f of p, that means the supremum of the set must be less than or equal to f of p. Right, A is the least upper bound of this set, and this is an upper bound, so A is less than or equal to f of p. And obviously what we wish to show is that that A is equal to f of p, right? So we will show that the limit as x approaches p of f of x equals A. All right, so let's let epsilon greater than 0 be given. Let epsilon greater than 0 be given. Now, A is assumed to be the least upper bound of the set. So A is the supremum of the set f of x such that x is less than p. And so there exists some x naught less than p. There's going to be some value x that's less than p such that the least upper bound A minus some value, this given value epsilon, is less than f of x naught, which would be less than or equal to A. Right, so you've got the supremum A, and we're going to create a tiny little left-hand interval near A. And there's going to have to be some x in here that produces an f of x that's within that interval. Okay, straightforward, right? And so therefore, if x naught is less than x, which is less than p, then A minus epsilon will be less than f of x naught, which will be less than or equal to f of x, which will be less than or equal to the supremum of the set. And then from this, it follows. From this, it follows that f of x minus a less than epsilon for all x, wherever x naught is less than x, which is less than p, right? So if I've got some x naught, so I've shown that f of x naught is between a minus epsilon and f of x. So then any other x will fall into that same interval, right? Okay. And so if that's the case, by definition, the limit as x approaches p of f of x must be a, right? That's just what this bit right here says. Okay, and then we can do kind of the same thing from the other direction. Right, and I'll do it just a little quicker. So similarly, we could say that f of p would be less than or equal to f of p plus. This is the right-hand limit, which would be equal to the infimum of f of x such that p is less than or x is in I. Okay, right. And so similarly, you could kind of set the same thing up. All right, now what about the p and q business, like the last sort of statement? Okay, so let's assume, right, so that's kind of the first that's a big inequality. And what about the p and q? So let's assume you've got some p less than q. Then what do you got here? Well, f of p plus, the limit of f as we approach p from the right, is equal to the infimum of the values f of x such that p is less than x, right? Which this would be less than or equal to the infimum of f of x such that p is less than x less than q, right? So this is just, so q is so this is just kind of constraining that a little further, right? And then you've got that's less than or equal to the supremum, same set, f of x, except here we're saying, well, it's the same set actually, p less than x less than q, which would be less than or equal to the supremum of f of x such that x is, less than q. And this, of course, the supremum of this, where x is less than q, is going to be the left-hand limit of f at q. Okay. And so that's the result. So this is just, let's just think logically about what these sets are. Let's break it down. So this infimum of f where p is less than x, that's just the right-hand limit. And that's got to be less than or equal to the infimum of f for all the x's between p and q, right? And then that has got to be less than or equal to the supremum of all the f of x's where x is between p and q. And that has to be less than or equal to the supremum of all the f's where x is less than q. Okay, and so then that's just the left-hand limit. Perfect. And so that is the result for that. Okay, very good. Very good. Now, the last section here, what we want to do is we want to, and this is something that'll come up later in the course, but it's also just kind of an interesting construct. So what we want to do is we want to show how we can construct a monotone function where we decide where the discontinuities are, if there are discontinuities. Okay, and so we're aiming to show that given basically any countable, finite or countable set, it can be an infinite set as long as it's countable. Any finite or countable set A on an interval AB, we're going to show that there exists a monotone increasing function on AB that is discontinuous has prescribed discontinuities, but is continuous everywhere else. Okay, so we wish to show that given any finite or countable set A of an interval AB, there exists a monotone function, monotone increasing function in our case, but we'll just say monotone. There exists a monotone function f on AB that is discontinuous at each x in A and continuous everywhere else. Right? So you give me an interval A to B, and you give me a finite or countable set A. And what I can do then is I can build a monotone function, that monotone increasing function, we'll say, on that interval that's defined everywhere on that interval. It's monotone increasing, defined on that interval, and is discontinuous at every x that's in the set A, at every x in A. And everywhere else it'll be continuous. Okay, and so you may be thinking to yourself, how could such a thing be built? Well, it's going to use something like the kind of function we saw with the greatest integer function, right? So how to build. And the fact that such a thing exists is really going to be the point of the last theorem, and rather than prove it, we're just going to show you how to build it. How to build. Okay, so let's say we'll start with a finite set, but you'll see that the construction can be extended to a countable set as well. So we'll start with the set A, and we'll say that it's finite. A1, A2, AN, finite. And that's just because it just makes the setup a little easier, but it's trivial to extend it to countable. Right, and we'll assume A is a subset of an interval AB that you're also given. So you give me the interval, you give me a subset of it. I can create a monotone increasing function that is discontinuous at every element in the set and continuous elsewhere. And so really kind of the heart of this function is another function called the unit jump function. And this is a simple function. Okay, so we'll denote it with an I. That's the name of the function. I is a function on the real numbers, R to R, right? Defined by I of x is equal to 0 or 1, and it's equal to 0 if x is less than 0, and it's equal to 1 if x is greater than or equal to 0. Okay, so it's a simple thing. What does this look like? Well, it's just, so here's your x-axis, here's your y-axis. It's 0 down here, got a hole there, and then it just jumps up to 1, and then it's 1, right? So it's cruising along. This is supposed to be a hole, and then it jumps up here and cruises along that direction. Okay, and so we can see here that the limit as x approaches 0 from the right-hand side is 1. Okay, and that's also equal to I of 0. And the limit as x approaches 0 from the left-hand side is equal to 0, right? So it's got this jump discontinuity. That's why it's called a jump function. It's the unit jump function. It jumps up 1 unit as you go from left to right. Okay, and this can be easily extended by just re-expressing it. So this is kind of a point, not tremendously helpful because it's kind of stuck here at, the break point is at x equals 0, but we can easily extend this definition to make it much more versatile. So we'll say then for a real number, we can set I sub a of x, right? So this is the unit jump function subscript a, right? So indicating that there's some involvement by the real number a. Really, it's just equal to the unit jump function where the argument, instead of just x, it's x minus a, right? So this is x minus 0, so we can make it x minus anything. And so instead, this is going to be equal to 0 or 1, and instead of the value being triggered on 0, it'll be triggered on a. So it'll be 0 whenever x is less than a, and it'll be 1 whenever x is greater than or equal to a. Okay. So this is just a modification of the unit jump function to allow it to kind of shift left and right on the x-axis. Okay, and so for example, we'll say, what about I5 of x? Well, that's just I of x minus 5, and it would be 0 or 1, and it's 0 when x is less than or 5, and it's 1 when x is greater than or equal to 5. Right, so this is just the same thing, it's just shifted over. 1, 2, 3, 4, 5. Right, so it's 0 all throughout here, and then it jumps up, and it's 1. Okay. So I sub ax has a jump discontinuity at a. Okay. So I sub ax has a jump discontinuity at a. Okay. So very similar to I sub 0 or just I, except here we have a jump. Okay. Okay, so we've got this thing. Now, so here's how we want to define our function. Here's how we're going to define our function. So let's suppose that if your a set is, so a is equal to a sub 1, a sub 2, dot dot dot, a sub n. We let this other set be just constant, c1, c2, dot dot dot, cn, and there can be as many. Well, these can be anything you want. They just have to be n of them. Okay, and so given you've got all these points where you want the discontinuities, you're going to have some kind of a constant value, and they can all be 1s if you want, but they have to be positive. So this is a set of positive real numbers, non-zero and not negative, positive. And so here's how we define our function. So f of x then is just equal to the sum for k equals 1 up to n of ck times I of x minus ak. Yeah, so this function here gives you exactly what you want. It gives you a monotone increasing function with specified discontinuities, these guys. Okay. It gives you a monotone increasing function with specified discontinuities, and these are going to be jump discontinuities. Let's take an example here and see how this kind of works. And so let's look at a simple example here. Grab more paper. Okay, so an example. This is a simple example. Let's let A equal the set 5, 10, 15. And let's use coefficients 2, 4, and 6. It doesn't matter what you pick here, just so long as the CIs are greater than 0. Okay, so what's the function look like in this case? So f of x equals the sum from k equals 1 up to 3 of ck I x minus ak. Right, so let's actually write it out here. So so c1 would be just 2, and then it's I times x minus a1, which is 5, plus 4 times I of x minus a2, which is 10, plus, and then I guess the last one would be 6 I x minus 15. There we go. Okay, so this is the function. And we'll just say for, assume the interval is maybe 0 up to, infinity, whatever. We'll just say 0 to 100. It doesn't really matter, but okay. And so let's plug in some values here. Let's see what f of 1 is. If I plug 1 into this function, what do I get out of it? Well, it's 2 I of 1 minus 5 plus 4 I of 1 minus 10 plus 6 I of 1 minus 15. Right, and so that's 2, and then I of 1 minus 5 is I of negative 4, so that would be 0. Right, so this is just 0. Plus 4 times I of negative 9, so again, that's less than 0, so that's 0. Plus 6 times I of negative 14, so that's 0 as well, so this whole thing is 0. And we're just going to plug in some of the key values here. And so if you plugged in 2, you would get the same thing. If you plugged in 3, you get the same thing. 4, same thing. In any real number in between, any decimal number, 3.762 would give you 0 as well. But what happens when we plug in 5? Right, so here I've got 2I 5 minus 5 plus 4I 5 minus 10 plus 6I 5 minus 15. So this is 2I of 0 plus 4I of negative 5 plus 6I of negative 10. Right, and so this guy here is 2 times 1. Right? Plus 4 times 0 plus 6 times 0. And so here I actually get a number 2. Okay, and then it turns out that if you plug in 6, you'll also get a 2. If you plug in 7, you'll get a 2. 8, you'll get a 2. 9, you'll get a 2. All the way up to, but not including 10. If you go 9.9999, you'll get a 2. Right, and what happens at 10? Well, at f of 10, you would actually get a 6. And that's going to be true at F11 as well, F12, F13, and F14. And at F15, you plug that one in, just try it, you'll get a 12. And then for all x greater than 15, f of x is equal to 12. Okay, so what's this plot look like? Well, I can draw it quick. It looks like this. So we'll say that's 5, 10, 15, 20, so on. And then we'll say 2, 4, 6, 8, 10, 12. Right, so between 0 and 5, we're 0. And then we got a hole, and then it jumps up to 2. And then from 5 to 10, it's equal to 2. And we have a hole at 10, and it jumps up to 6. And then from 6 to 15, from 10 to 15, it's equal to 6. And then we got a hole, and then it jumps up to 12. And it's 12 for the rest of the interval. Right, so again, obviously a monotone increasing function, non-decreasing, basically. And discontinuities at 5, 10, and 15, just like we wanted when we specified up here. Now the choice of coefficients is completely arbitrary, doesn't matter. You can just see that the 2 jumped up to 2, and then jumped up to 4, and then jumped up to 6. They're going to be the coefficients will drive how what the jumps look like. Okay, so that is an example of this kind of function. Now, what properties does the function like this have? So let's just kind of draw a nice picture here of what something like this looks like. So it's 0, you got a hole, you got a jump, and then it does this for a while, and then it jumps up again, and then maybe it jumps up for the last time and just kind of continues on. So it kind of looks like this. So what is this function? What are the properties? Well, it's got nice properties. One, it's monotone increasing. Right, so if you specify the uninterval, you build this function as designed, as desired, it'll be monotone increasing on that interval. Notice it's continuous everywhere outside of the set A. It's continuous outside the specified set. Okay. And it's got a jump discontinuity everywhere in A. All right, so there's a jump discontinuity here, here, and here. So this would be like your A1, A2, A3. Okay. And then it's also, we can say something about these continuity or these jump discontinuities. There's actually, you can see how it's constructed. You have right continuity at each of these jumps, right? So it's right continuous for all x in A. All right, so we're right continuous at A1. So if I approach A1 from the right, I'm continuous there. If I approach A2 from the right, I'm continuous there. If I approach A3 from the right, I'm continuous there. Okay, and so these are the properties of this function that we've designed. Okay. All right. Now, as I said, there's a nice theorem that goes with this function. I'll state the theorem, but I want to do a slightly more challenging example quick, just to show you how this can look with functions that are not so simple. All right, and then I'll state the theorem, and the theorem will be used elsewhere. We won't prove it because it's largely just the construction we just did. So let's let the C of n constants be equal to 2 to the negative n. And let's let x of n equal 1 minus 1 over n plus 1. And here, the x of n's are going to be for all natural numbers. So for n equal to 1, 2, dot, dot, dot. Okay. Right, and so these are where you're going to have your discontinuities. 1 minus 1 over n plus 1. Okay, so 1 minus a half, for example, you'll have a discontinuity. That's 1 half. Okay. And let's assume the interval that we're interested in is, so AB here is 0, 1. So this is going to be a lot of rational numbers inside of 0, 1. So here's the function again. F of x equals the sum n equals 1 to infinity of c sub n I of x minus xn. So this is the function we just designed. Now, one thing to notice here is that for our xn's here, they satisfy, so 0 is strictly less than x1, which is 1 half, which is less than x2, which is what, 1 minus 1/3, so 2/3, which is less than dot dot dot, less than xn, less than dot dot dot, less than 1. Right. So these things are ordered, right? They're ordered in this way. Okay. So this is the function, and so let's plug in the actual pieces of the function here. So this would be equal to the sum from n equals 1 to infinity. Now instead of cn, I'm going to put 1 over 2 to the n. Okay. And then I of, this would be x minus, and then x of n is this, so to x minus 1 over n plus 1. All right, so we can clean this up a little bit. N equals 1 to infinity, 1 over 2 to the n. And then I of, so this would be minus 1 plus, well, let's write it out. This would be x I of x minus, so this would be n plus 1 minus 1 over n plus 1. So this would be just n over n plus 1. All right, so it looks like that. All right, and maybe that's helpful, but actually it might be easier to work with it from this standpoint. But now you could do some work, and you could see that, so whenever x is between 0 and 1/2, the value of the function is x1, right? So then I of x minus xn is equal to 0, right? So f of x is just equal to 0 whenever x is in the interval 0 to 1/2, open. Okay. Then we could say that if x1 is less than or equal to x, which would be less than or equal to x, which would be less than x2, which would, if you look at here, that'd be 2/3. Then I of what, x minus x, x minus x1 equals 1, and I of x minus xk is equal to 0 when k is greater than or equal to 2. So f of x would be equal to c1, which would be 1 over 2 to the first, 1/2, for all x in the interval 1/2 up to 2/3, right? So you can kind of just reason about what the value of this function would be. And then we'll go one more step. If x2 is less than or equal to x, which is less than or equal to, I believe, 3/4, which would be x3, then let's see, I of x minus x sub k would be equal to 1 for k equals 1 and 2, and I of x minus xk would be equal to 0 for k greater than or equal to 3. And so in this case, when x is between x2 and 3/4, f of x would be equal to c1 plus c2, right? So you got these two, which would be equal to 1/2 plus 1/4, which is 3/4. And so x would be in, and that's the value of f when x is between 2/3 and 3/4. Okay, right, and you could continue on like this, but let's just jump to the picture. What does this look like? I'll try to draw a reasonable picture of this because it's pretty cool. So here's 0, and then somewhere out here is 1, and then in the middle, dead center, you got 1/2, and then 2/3 would be like here, and then we'll say 3/4, and then 4/5, right? And we could keep going, but we're not going to. And then on the y-axis, you've got 1/2 here, and then 3/4, 4/5, etc. And so for all the x's between 0 and 1/2, the value is 0, and then we've got a hole here, right? So we've got all of these guys. And what happens here? We just said it jumps up to 1/2, doesn't it? So it jumps up to here, and that's good through 2/3. And you got another hole, and then it jumps up to 3/4, right here, to right there. Sorry, that's a hole. All right, and then it jumps up again. and then it jumps up again. It keeps jumping up, and the height of the jump shrinks down, right? And the length of the gap for the values jump down. So you can see this thing here is going to kind of taper off here, and you'll have a limit up here at 1, right? So they'll approach 1, but they'll never get there. Right, so the intervals shrink basically up and to the right as n approaches infinity. They shrink up and to the right as n approaches infinity. Okay, so that's kind of a cooler example of building a monotone function on an interval. In this case, with an accountably infinite number of discontinuities, right? And the discontinuities are prescribed, like you know exactly where they are. Okay, and all the other properties still hold. It's continuous everywhere else. Notice it's continuous here, it's continuous here, it's continuous here. It's just discontinuous at the jumps. It's also right continuous at each jump. Okay, and obviously it's monotone increasing. Okay. Very cool. So this is a cool example. Okay, so all of that is for the following theorem. So those were examples building such functions. But here's the theorem. Let's let a and b be real numbers, and let x of n, natural number, be a countable subset of AB, the interval. Let's let C of n equals 1 to infinity, be any sequence of positive real numbers such that the sum n equals 1 to infinity of Cn converges. So here we have to have a converging set of Cn values. And so what the theorem says is that then there exists a monotone increasing function f on AB such that, we have a couple of properties here, such that f of a is 0, and the value of f of b is equal to the sum of n equals 1 to infinity of Cn, right? So the Cn values, whatever they converge to, that's the value of the function at the right side of the interval, right? So look up here, right? You can see that that's would be the case here. The Cn's are all going to converge to 1. Second property is that f is continuous every outside of the jumps. So it's continuous on AB minus the values xn, n equals 1 to infinity. So it's going to have infinite discontinuities, but everywhere else it'll be continuous. The third property is that f of x sub n plus equals f of xn for all n, right? So the function is right continuous at all of the discontinuities. And then the fourth property is that f is discontinuous at each xn. Right, so specifically the discontinuities will be equal to the value Cn. So for example, f of x sub n, if I subtract the left-hand limit from f of xn, I would get the jump. Right, so basically if I subtract the left-hand limit, if I subtract this value from this guy, that's the jump. Okay, and so those are the four properties. Okay, and so we'll use this theorem later on in the course, but it's also just kind of a cool theorem, and it just encapsulates all of the things that we just discussed with our example monotone function. The proof of this is largely based on the construction we just did. Of course, you would have to prove some of these properties hold, not simply draw a picture, but you can imagine how it would work. All right, I think we'll leave it there for now, and then when we come back in the next section, we'll get into differentiation. So we'll be shifting gears a bit and talking about derivatives and some of the famous theorems of differentiation, but from the standpoint of real analysis. All right, take care.